Good morning and welcome to EcoMotion's webinar on Microgrids, Resiliency, and PERCs. This webinar is organized by the Local Government Sustainable Energy Coalition, or LGSCC, in partnership with EcoMotion. My name is Grace Kaufman. I am a project associate at the Local Government Commission, serving as the coordinator for LGSCC, and I will be your moderator for this webinar. A quick overview of today's agenda. I will provide a brief intro to LGSCC for those who may not be familiar with us, then on to our feature presentations. Before we get started, I have a few logistical items to go over. Everyone will be muted except for our panelists. Due to the large number of participants, we ask that you type your question into the question box. Please feel free to submit your question at any point during the webinar. I will be summarizing these questions during the Q&A portion, which will follow the presentation. Any of the questions we don't get to, we'll ask our presenters to respond to after the webinar, and we will share their responses in a follow-up email. For those wondering, this webinar will be recorded and made available on our website along with the PowerPoint presentations. And as I mentioned, this webinar is being organized by LGSCC, which is a network of local governments and their allies from across California. LGSCC is the entity that represents local governments at regulatory proceedings. Each month, LGSCC provides a comprehensive debrief of regulatory updates for its members. Together, we work to advance energy action and increase local capacity to build community resilience. The Local Government Commission serves as the program administrator for LGSCC. LGSCC is working to expand our strong peer-to-peer network of sustainability practitioners and to formalize mechanisms to exchange knowledge and tools. Through our advocacy and engagement, we are working to bring integrated energy solutions and resources to local governments across the state. If you have any questions or if you're interested in joining LGSCC, please don't hesitate to reach out to me. Now on to our presenters. Ted Flanigan is the founder and president of EcoMotion. Born in New York City and raised on Long Island after graduate school, Ted worked as a strategic planner for the New York Power Authority following his passion for energy efficiency. In 1998, Ted came to Los Angeles to serve as Director of Energy Efficiency for Los Angeles Department of Water and Power. He was then Managing Director of the Energy Coalition, running innovative efficiency programs for California utilities. He then worked for the World Bank's International Finance Corporation, managing a lighting transformation project in the Philippines. In 2001, Ted formed EcoMotion with the guiding principle of the power of the increment, that small actions collectively make great sense for a local, regional, national, and global society. Ted publishes and lectures on a broad range of energy and environmental issues and policies. Michael Ware joined EcoMotion team in 2007 to be an honest broker of solar power systems. Prior to working at EcoMotion, he worked at Perma-City Solar. At EcoMotion, Michael's work focuses on solar opportunities, measuring potentials, and developing solar implementation strategies for organizations as diverse as Kimco, CBS, Sempra Utilities, LA Metro, and the Orange County Great Park. As an expert in utility rate structures and how they impact the return on investment of a given investment, Michael has developed tools for weighing the value of different components and comparing different scenarios. Michael has developed particular expertise in analyzing and comparing solar bids. His responsibilities also include solar findings to both expert and less experienced stakeholders to facilitate decision-making. Now I am going to hand the mic over to Ted, and a quick reminder to all participants to please type your questions into the control panel at any point during the presentation.
Thank you very much, Grace, and welcome to the webinar. EcoMotion is pleased to share a 6-site microgrid case study with you, and most importantly, to share lessons learned along the way. My name is Ted Flanigan. My colleague Michael Ware will be our co-presenter. So let's dig in. The Santa Rita Unified School District story, microgrids, resilience, what we call PERCs. We're going to be talking about microgrids, defining microgrids briefly, looking at their elements, the values that they provide. We're not going to show a video. We had planned to, but given some of the technical limitations of the webinar, we think it's better that we just give you the link to the video and you can watch it if you're interested later. It's a 6.5-minute video. We will dive into the Santa Rita story, where we go through how this all came about, the basic design, sizing the system, looking at what we call the perfect storm. We'll discuss rate components and solar and battery locations, financing, construction, and the long-term benefits of the PERCs, or what we call the PERCs, the Powered Emergency Response Centers. We'll then shift to scaling the model, talking about how this is applicable to other school districts without solar and those with solar. And we also we'll look at taking the model to cities, universities, hospitals, and other kinds of institutions. We'll talk about bringing PERCs to the Campbell Union High School District up in San Jose, which has solar. We'll talk a little bit about our grant process there. And again, we'll get into lessons learned and leave time for questions and answers at the end of the presentation. A little bit on EcoMotion. Our mission is the cost-effective greening of cities, corporations, and campuses. We have been an owner's rep for different clients, cities, corporations, and campuses for our 12-year run. We're honest brokers. We have no industry ties. And generally, we're very passionate about what we do. We've run the Solar Santa Monica program for the past 12 years. We've run utility programs for Burbank and Anaheim. We're the solar consultants for the LA Metro system. We're involved in a 1.5 megawatt solar addition at a large company down in Orange County. We're the carbon neutrality advisors for a school back in New York State. For the past 5 years, we were Prop 39 managers like lots of other energy consultants in California, and we worked with a number of school districts and charter schools and managed and prioritized the energy efficiency opportunities for over 130 campuses. We take great pride in demonstration projects. Those of you that have been to the Long Beach Airport may know our 6 dual axis bifacial panel trackers that are there. We've done efficiency partnerships with Edison and PG&E and the gas company. We've worked in Florida at Miami City Hall. We've partnered with Gensler Architects to design solar ports that have won architectural records. And we're most proud of our Save a Ton student rallies, where we teach kids about how to take action and the power of the increment that Grace mentioned. We have a huge display called the Emissions Time Bomb, 34 feet tall, that represents 1 metric ton of CO2. We've taken that out to lots of school sites around California and actually all the way across the country. So very briefly on microgrids, I think most people have become quite familiar with microgrids in the past few years. It's been enabled in large part by the rise of distributed storage and cost-effective distributed storage, thanks to what I call the lithium ion revolution. But basically a microgrid is generally connected to the electric grid, but is able to island in the event of an outage. So you can see you have a boundary around a certain amount of buildings or a building, and that is your microgrid that can island in the event of a power outage. A microgrid is a group of interconnected loads and distributed energy resources within a clearly defined electrical boundary that acts as a single controllable entity. A microgrid can connect and disconnect from the grid to enable it to operate in both grid-connected or islanded modes. Microgrids are not autonomous, they're not off the grid. In fact, they receive great value from the grids, and as we'll talk about further in the presentation, they provide great value to the grids and will in the future. So there's 4 fundamental elements of carbon-free microgrids, and we're only talking about carbon-free microgrids. Microgrids have been in operation for many years using fossil fuels, but our passion is carbon-free microgrids. But the first element is the controller. That's the brains of the system. It's literally a small laptop computer in size, typically tucked into an energy storage cabinet. Distributed energy, we're talking solar, but could be wind or other kinds of renewable resources in different parts of the country or the world. Distributed storage is the third element. And again, batteries are used in this case to store for daily use and emergencies. Distributed storage is very expensive. So one of our challenges, and Michael's going to talk about, is making sure that we have the right amount of storage, but at a cost-effective amount of storage. And the energy management system is critical because it controls demand during outages. And we'll talk a little bit about controlling curtailable loads and maintaining critical loads on site. So in the event of a grid outage, a big switch is thrown and all of a sudden the grid is an island and it is operating with its own energy resources, its own storage resources, and its own controls. Microgrids have been around for a long time. The first power station in the United States, Thomas Edison's Pearl Street Station, was fired up in 1882. It had an initial load of 400 lamps at 82 customer sites. Well, contrast that with one of the most celebrated microgrids, Co-op City, as in the Bronx and in New York City. It is a housing complex that houses 60,000 residents, has 34 towers, townhomes, shopping centers, movie theaters, high school. It's really a city, as its name suggests. And during Superstorm Sandy, or Hurricane Sandy, which turned into Superstorm Sandy, it remained operational throughout the storm. It was one of the very few places in New York City that had light and had power, and its residents were comfortable. In its earliest days, it had a large central heating plant and a backup generator. Then in 2001, thanks to combined cycle technology, natural gas, highly efficient natural gas technology, a tri-generation plant was commissioned that provides heating, cooling, and power. And this microgrid is not only an example of resilience, but it's an example of a profitable venture that's providing $15 million of benefits to that city, to Co-op City per year. There's a picture of the cogeneration plant. Grids work at different scales. I like to think of the macro grid as being the utility, and then microgrids can be at a community scale or a neighborhood scale or a building scale or on a ship or what have you, with decreasing voltage typically as you get smaller and smaller. Had the fun of visiting a microgrid on Cuttyhunk Island in Massachusetts a couple of summers ago. We boarded a shipping boat out of Menemsha and Martha's Vineyard and headed across to Cuttyhunk, which is a fascinating case study. It's an island that was owned by a family for many years. Now they have some homes on it. The population goes from about 6 in winter to 250 in summer. They have 174 meters. They have a peak demand of 250 kilowatts when everybody is staying at the hotel, and they have shore power for yachts coming in. But this community had been paying 60 cents a kilowatt hour for power, for diesel-fired power, after it got a $2.1 million USDA grant. It put in 350 kW of solar, 1.25 megawatts of battery storage, and now it is operating at a lower cost with actually in a carbon-free mode. A couple other celebrated microgrid case studies to sort of show the scope. Many of you have probably heard about the Brooklyn Microgrid project and Lawrence Orsini, who's pictured here. He's created this microgrid within a dense urban area, and he's using blockchain technology to account for all of the transactions. So peer-to-peer transactions through the installation of transactive grid element devices. Blockchain technology accounts for transactions, managing sales and purchases. Prosumers generate smart meter tokens, and they're sold to neighbors. So far, more than 130 buildings are in this very pioneering and very innovative microgrid. Another one that you might have heard is Stone Edge Farm up in Sonoma County. A couple that moved up there to create a vineyard, has a 16-acre organic farm, goals to cut its carbon footprint, put up 7 different solar arrays with combined 300 solar panels, has 4 different types of batteries, capstone microturbine, an electrolyzer to create hydrogen fuel for the Toyota Mirai that they have, which is a hydrogen fuel cell vehicle. Other celebrated microgrids include Harvard University, Princeton University, New York University, and Alcatraz Island. And microgrids all have different objectives, but there are multiple benefits, multiple values of microgrids. First off, energy resilience for short-term outages, energy supplies during natural disasters, carbon-free operations. Microgrids help to manage the integration of renewable energy on the grid. They help to reduce greenhouse gas emissions. They allow for increased use of storage, electric vehicles, and distributed energy resources. And as we'll talk about, they can provide grid and ancillary services support. This is a shot that you might want to take a screenshot of, or a slide that you might want to take a screenshot of. We've completed a video on the Santa Rita story last month. It's a 6.5-minute video. It features Jigger Shaw. It features the professionals that put this system together from Sharp, as well as the school district. And it's an inspirational video that matches this presentation. So now we're going to dive into the Santa Rita Unified School District story. Santa Rita Unified is located in the city of Salinas, up in Monterey County. Salinas is the salad bowl of the world, and you can see on this slide, in the middle of the slide, you can see one of the campuses, and you can see that it abuts the fields there. SRUSD at a glance. There's 6 school sites, a small district, 4 elementary schools, 2 middle schools, a district office, serving students from Monterey County, a largely Hispanic student body. EcoMotion was retained in October of 2015 as SRUSD's energy consultant. EcoMotion was hired to help SRUSD to get batteries. The school district wanted students to be able to shelter in place during outages. When I got a call from the school district, it was explained that staff and board members had heard all about Elon Musk and Tesla's Gigafactory. They were aware of what EcoMotion calls the lithium-ion revolution, that there now are cost-effective battery solutions. And the school district said that it wanted batteries to cover 7-hour school days. So if the grid went down at 8 o'clock in the morning, it wanted to be able to keep the kids on campus, learning in school and safe. EcoMotion was retained to find a solution. I frankly didn't think that we would find a solution. I thought that the goal of battery storage covering 7-hour school days was untenable. As most of you know, almost all energy storage in the state of California is 2-hour garden variety storage. That's what the SCHIP incentives are set up for. So we decided to go ahead and tabulate average loads to determine how much capacity would be needed and at what cost to achieve the school district's objective of just energy storage, of just batteries in isolation. And you can see from this slide, again, this is based on average peak demand during school days, that we realized that the school district would need about 383 kW of capacity and 2,681 kWh of energy storage for its 6 campuses. And we thought that that would carry a price tag of somewhere between $3.5 to $5 million in batteries. And frankly, I thought that was the end of the day and that the school district would just say, thank you very much, we don't have that kind of money to spend. The district had $750,000 in Prop 39 money that we ended up using for another purpose. So I'm going to credit my colleague, Michael Ware, who's going to take over here in a couple of slides, for the solution. Because he realized that this school district that never thought that it could afford solar, and it was never really a priority to have solar, but that solar could become a tool for the school district, and that we could put enough solar on campus to cover 100% of the district's power bill. And that if we did that, and we could execute a rate switch in the PG&E rate schedule, that the savings from solar would pay for the storage. And the combined package between solar and storage could potentially be rolled into a power purchase agreement. So we put out an RFP to a number of firms, and at the end of the day, SolEd Benefit Corporation offered a PPA for the integrated system at parity, at the same price on an annual basis that the school district had been paying for power before, a 24.18 cent PPA with a 0% escalator. SolEd agreed to build about 1 megawatt of solar ports on these campuses, plus a little over 1 megawatt hour of energy storage, so that integrated microgrids could island during power outages. The Prop 39 funds were used to pay for advanced energy management, to control curtailable loads during perfect storm scenarios. So now I'm going to pass the microphone to my colleague, Michael Ware.
Thank you, Ted. And I'm going to talk about basic design steps, how we approach an opportunity like this and some of the considerations we give. So the first thing we do in determining the solar potential for a site is to look at vacant ground areas, rooftops, parking lots. We're wondering where we can locate parking structures, carports, Tracking systems could be in a ground mount. So for example, here's a slide showing a ground mounted system at Portland Community College. And this is an ideal location for ground mounted systems as long as you know that this is going to be available to you for 25 years. That's what we consider the minimal life of a system. So you would want to put it somewhere where you don't need to move it. And these happen to be rows of fixed panels. But if you imagined a pole on the long axis, they could turn and track the sun. So you see that sometimes too on ground mounted systems. Here's a great picture of a parking structure. This covers a single row. They're also made to cover, well, this is a double row actually. They're also made to cover single rows. And this particular one has special approval to be incorporated in schools in California. But the carports, in addition to providing energy, is a great place for shade, very appealing on a hot summer day, and it's a great place for parking lot lighting. So some extra benefits for those people who have the parking structure potential. Here's a good shot of a system on a roof. The ideal roof is sturdy. It's new enough to last 5 years. Again, you want to put your solar life on the same span as your roof life, because it would be very costly if you had to, pick up the solar system to re-roof and then put it back down. So that's one thing that we look at, and sometimes we advise clients to go ahead and re-roof as you're putting on the solar, so you can put them both in concert. You see rows of solar panels there. They're held on trays and tilted toward the sun. The gentleman is working on a piece of equipment called the inverter. It's right there in the field of panels. That turns the DC power into AC power for the building. And if you look closely, you can see that these trays are weighted down by concrete pavers. So they don't have to penetrate the roof as much, and that can hold them down and create the ballast for the roof. So shade structures can also be placed over turf, over lunch areas, over maintenance areas. So they're like parking structures, parking carports, but you could put them anywhere. So we've seen them on the sides of sports fields, providing shade to the people who are watching. But it creates a great surface to generate power and create shade, so it can bring life to your campus or your location. Let's talk about a little bit of, in this example, here's a site at one of the Santa Rita schools where you can see where the lunch tables are set up. So it looks like a beautiful day, but couldn't they benefit from some shade? And so we specifically designed shade structures to go over those areas. And we know that those lunch shelters are already far more popular. The lunch locations are far more popular than they were before. So when it comes time to size the systems, you account for the space potential, the cost, the electricity load that you're offsetting, and the utility rate structure that's possible. You may be able to find one that you're not on currently. And as the slide says, the rates switch. Rates never sleep, they toss and turn, they're constantly changing, and so we look for those that can serve the case for the long term, and we hope that they stay in place. Now, when we addressed Santa Rita, we had specific battery backup goals, resiliency goals. And for that, you look at the load and the duration. So you've seen this slide before, but what we did is we looked at each campus during their school hours between 8 and 3, and we examined the whole year. We're looking at what we call interval data. So every 15 minutes, there's a snapshot of how much demand a location is using. So we use that to profile the average daily demand. And so from that, we computed how much storage and energy we needed to get them through 7 hours of the day. And so, for example, the top example, Bolson Knolls Middle School, they needed 504 kilowatt hours. And one thing that you have to consider, in addition to the size of the battery storage that you're providing, is how solar generation works. If you're putting solar into the equation, you have to be aware of when solar is abundant and when it is diminished. So you can see here that June and July have more than twice the amount of solar generation as January or December. And so you factor that into the equation as to, you have to look hard at the minimum times that you're going to have solar. For an example, let's dive into the Bolsa Knolls example. We examined for each month out of the year, what their average load was, how much irradiance allowing solar generation there was likely to be, and how much energy we could bring to the school. So their basic goal, as we recall, is 504 kilowatt hours. That's on the bottom line. And then the next to the bottom line, you see between the different months how much storage plus energy we think is available. In the middle line, 216 is the constant amount. The amount of batteries, that's going to be a constant. So every month you're going to have an average of 216 kW available. But for the solar generation, that's going to vary. So in January, we see we barely squeak by. We think we need 504 and we think we can count on 606. In May and June, you can see it's quite abundant, and so we don't think that we would have any problems in terms of meeting the energy needs for the school on those days. Now, one thing that gave us confidence was developing the storage probability matrix. And we used existing data, weather data. You can profile expected solar generation, for a whole year and look at what you've got. And so we wondered, how many days are we likely to reach our goals? And you can see there in the high 80s and 90s for creating at least 7 hours of storage. The top example, Bolsa Knolls, 94% of the time we're likely to meet our goal of getting them through a whole day. And failing that, there's a 98% chance, adding the first two columns, that we have at least 6 to 7 hours of storage. So we feel that based on weather patterns in the area, the amount of sunshine, the solar capacity, et cetera, that this is very achievable. But we do have to address what we call the perfect storm. And our version of the perfect storm day is when we have less solar energy than we'd like. You see that the perfect storm would entail the students arriving, and the grid goes down at right away at 8:15, and it's rainy and it's dark. Now, so we know we're not going to have a lot of solar energy to assist the situation. That's when we go into what we call battery mode. So we're being very conservative. Any load that is curtailable will be curtailed. The air conditioning is on wireless control, so that can be dialed down. Plug loads can be turned off. In fact, there's a whole regimen in terms of reducing what you can. And only the critical functions would continue. Lighting, communications, refrigeration. This slide talks about how you would differentiate between the loads that you need, your critical loads, and those that you can control. When the grid goes down, there's a period of time where the microgrid clicks on, and during that time you can be ready to reduce the loads that you don't critically need that day. You can dial down the air conditioning, the lighting, turn off unnecessary things for that moment, like the pool pumps. You can unplug things to solve the plug load, and make sure that available energy is going towards the things that you really need, like lighting and communication and refrigeration and so forth. Now, we found that if you tried to hardwire this and had everything controlled by an energy management system, that would be cost prohibitive. So we kind of share the responsibility between some wireless controls and a lot of voluntary and a response by the school district. In fact, they'll have drills as to how they're going to reduce their loads on campus. Now we look at the rate component, and the rate component lets us know a lot about the financial state, how much solar is going to save them on their bills and how they can apply that to their needs. There are many different utility rates out there, and some are friendlier to solar than others. So to have a basic understanding of electric rates, and this is true of most utilities across the country, they divide their bill charges between two basic charges. One is called demand charges, and the other is called energy charges. So energy charges relate to kilowatt hour charges. Demand charges relate to the amount that you pull at any one time from the grid. So there are two, and they behave differently in terms of solar. So for example, because of net energy metering, when you generate a kilowatt hour, it either immediately displaces one that you would have drawn from the utility, or it's kept as a credit at full retail value, or pretty close to full retail value, that you can apply to your bill later. So that's why you can reliably offset your energy charges. But demand charges are different. So let's say that your campus or your building has its highest demand at 8 o'clock in the evening. Well, that's outside solar hours, so that's not going to be reduced by solar. Or let's say it happens at 8 o'clock in the morning as you're turning everything on. Solar is just beginning to get active and is not going to impact that. Plus, you have 30 days in a month, and chances are that in many times you'll set your peak outside of the solar hours. So you have to understand how that bill will be impacted by solar. So this is a specific comparison between two rates that happen to be in the PG&E area. The one column, A10, TOU stands for time of use. That is one that has both energy charges and demand charges. So you'll see at the top, the summer peak kilowatt hour, for example, it's 21 cents for every kilowatt hour you use. And the bottom is the demand rate. So that's $16. So let's say that your peak demand was 300 kilowatts. Well, that's almost $5,000 worth of demand charges. Now contrast that with the rate structure next to it, where at the bottom you see that there are 0 demand charges. So the entire bill is going to be paid through the kilowatt hour charges. And that's why the top rate, the summer peak kilowatt hour rate, is at 54 cents, because they had to put a lot more charges on the kilowatt hour side. But here's the good news. This is how it works for solar, and how we were able to show the school district how they could use solar to completely wipe out their bill. So on the left, we're counting up the usage of the school. So every year they use 333,000 kilowatt hours. And based on this rate, that shows you that the bill would come to $78,000. Now, the next side, the other side, is the solar generation. And think of that like the credit. So whereas the use is the debit, the solar energy generation is the credit. And you can see that in the summer, they generated far more than they needed by generating 76,000 when they only needed 41,000. And so it led to a huge credit there of $41,664. So that allowed them to apply that to other portions of the year. So technically what solar allowed this school to do, you see only 262,000 kilowatt hours of generation were enough to offset the bill created by 333,000 hours of use. So it's like 80% of the generation wiped out 100% of the bill. So that's why it made perfect sense for them to move to this rate without demand charges, use solar to offset the bill, and it was a great opportunity for them. However, there were some issues with that particular A6 rate that was so solar friendly. One was that it was set to expire for some locations. The PG&E changed the rate so that it could only be used by locations that had less than 75 kW total. So we had to have the school go ahead and adopt that rate before the opportunity closed. So they had to take it about a year earlier than they wanted to. And in fact, because their solar wasn't in yet, they kind of lost the value of the solar generation for a year. But it was important to access the rate because they promised to grandfather it for 10 years. So that's why we urged them to do it. And just by the way, this picture of battery cabinets here represents about 203 kilowatt hours of storage, just so you get some idea of scale. So talking about solar system and battery locations, we provided a layout for each of the schools. This represents the 6 different school districts, schools in the district. And the blue shaded areas show where we were recommending the placement of solar. So you can see some is over the parking lots and some over the interior of the school and lunch shelters. And the arrows generally indicate the location of the electric room and where we would place the batteries. So just looking more specifically, for example, at New Republic School, the solar was placed over the parking lots. They only needed 163.8 kW DC, and the battery location would be right next to the meter in the front of the school. So that's how that school sized up. Gavilan View Middle School used a combination of carport structures and lunch shelter structures. And again, the battery location is sited closer to the electric room, and they needed 184 kW. And here's Bolsa Knolls Middle School, where in the interior of the campus, you see those 3 shaded areas. Those represent structures over lunch areas. And I think we proposed carport structures in the parking lot, but actually I think they moved it over to another asphalt playground area, which was better for them. And again, the battery location then would be close to the electric room in that particular case. So now I'm going to turn it back over to Ted to talk about financing and other measures.
Thank you, Michael. And financing was clearly one of the most challenging aspects of the project, and we didn't expect that at all, because when we had selected SolEd Benefit Corporation to be our developer, they had a company named C2SSG that was their financial partner, and we thought that once that PPA was signed that was a done deal. But in reality, we ended up with a PPA without financing. C2SSG was not willing to tackle the 7-hour batteries. And so SolEd approached another 17 financiers and talked to countless other professionals in the space. All of them were leery of financing resiliency. And I think this is a trend that we're all going to have to come to terms with, is that paying for resiliency is a new thing. Resiliency generally lacks a revenue stream. So there was a number of financiers that we reached out to: Altus Power, Blue Path Finance, Brightmark Energy, looked like they were going to buy the deal at one point, Candle 3, East West Bank, Renew Energy Partners out of Boston, US Bank, Wells Fargo. All of them looked at this, and at one point, Dave Kuhnhart, my friend Dave Kuhnhart, just said, the market is really just not ready for this. But we prevailed. EcoMotion and SolEd urged Jigger Shaw of Generate Capital to buy the project. Many of you know Jigger Shaw. He's a visionary in the solar space. He's considered the founder of the power purchase agreement. He founded SunEdison, which at one point was the largest solar company in the world. Jigger Shaw and his colleagues at Generate Capital bought the project and now are promoting the model. They see great value in resilience as a value added on solar projects. They were eager to take on a 24-cent PPA, but they insisted on bankable technologies and bankable project partners. So out went Avalon Batteries, a maker of vanadium flow batteries that the school district preferred. We think that's a safer technology, a NASA developed technology. And in came lithium ion batteries that have pros and cons. MBL Energy was brought in to build the systems. Sharp Energy Systems and Services Group and Black & Veatch were brought in, both multi-billion-dollar companies that have stellar reputations and great credibility. Our team negotiated the terms of the PPA and arranged that any future asset management values will be split. So what do I mean by that? Well, microgrids have potential secondary system revenues. Imagine now that it's 12 o'clock, the sun is shining, the batteries are full, and we have kids, we only have another 3 or 4 hours of the school day left that we might want to cover in the event of an outage. Well, then in theory, we can sell that unused capacity or that extra capacity to utility programs for demand response, automated DR programs. And there's also great opportunity here in the coming few years for systems like this, microgrids like this, to be aggregated together and for them to sell ancillary services to the independent system operator. And you know, frequency regulation is something that has to happen 24/7, all the time. And so there's all sorts of ancillary services that have been provided by power plants for years, and now microgrids may be much more nimble and cost effective in providing these ancillary services. And so it's the revenues from these opportunities, working with utilities and the independent system operators, that will be split with the school district over time. I mentioned MBL was our lead contractor. It's a woman-owned company. We're proud of that. Sharp is the asset manager, and it's bound to performance guarantees on both the solar and the energy storage. And EcoMotion wrote the performance guarantee for energy storage that we'd never seen one like this before. Black & Veatch engineered the microgrid system, and its credibility we think was essential in getting this fully permitted by or interconnected with PG&E. Obviously, everything had to be fully permitted by the Division of the State Architect. In terms of solar project facts, we did achieve with just over 1 megawatt of solar. We used 335-watt REC panels. We have over 3,000 of them. We had ideal inverters, string inverters, also energy monitoring systems at the schools. In terms of batteries, we ended up with a little bit over 1 megawatt hour as we had projected. We use Samsung batteries, 27 30 kW units. We use the Sharp Smart Storage solution. That's the microgrid controls. Long-term project benefits, and this is something that the school district never anticipated. You know, remember their original goal was to just provide power outage protection for their campuses. They never thought about, what would happen if there's a long-term outage? But PERCs will provide. Our powered emergency response centers will provide for the community, cell phone charging, EV charging, e-bus charging, potentially medical and triage support if need be, incident command centers, emergency sheltering if need be for the communities that they serve. This disaster preparedness is something that the school board is thrilled about. They had no idea that we were going to be creating this kind of a community benefit as part of this project, and that it would all be financed. It didn't cost them a dime to do this, and their utility bill is essentially the same as it was before they engaged in the project. So we've reached out to city and county officials, the fire departments, the police departments. We're working with the American Red Cross, developing protocols for prolonged outages so that we can turn over the campuses to the Red Cross if need be. These are teachable moments in Monterey. Every student, every teacher, every staff member is now fully aware of the solar systems, the carbon-free microgrids, and the islanding benefit. We're going to have battery mode drills on each campus. We're going to have energy wardens, just like we've had earthquake wardens. We're going to have energy wardens on each campus that are going to be responsible for plug loads and making sure that we curtail loads to whatever degree is required. We're developing student curricula for each grade level. The awareness program is being developed for parents in the community, and it's all linked in with electric transportation. So finally, what is the value of this PERC model? How can it be scaled? These PERCs have many benefits. They maintain student education. Students shelter in place where they're safe. Long-term community and first responder support benefits. So PERCs make sense for campuses without solar, like Santa Rita, and for campuses with solar. And there's about 1,000 in California, campuses with solar in California right now, and that number is growing fast. And virtually all of them, in the event of a grid outage, that solar capacity will be rendered completely useless. PERCs make sense for other sectors too, for city facilities, universities, business parks, waterworks, neighborhoods, what have you. So we took our program to Campbell Union High School District. Nancy Pfeiffer, who was really the visionary of this PERC concept, originally was working for Santa Rita, and then she moved up to Campbell. And Campbell is a high school district that has 3.7 megawatts of solar on its campuses. It invested $15 million in solar, and all the savings that that school district has achieved through the A6 rate that Michael talked about earlier are going back into their normal school funds and their normal operations. So Nancy wants to make these campuses resilient. We have a project goal of rewiring these campuses with storage and controls. Right now, I mean, the board there thought that if the grid went down, that they would have power, that they would have solar power. But as you all know, that's not the way these solar systems work. So we went out seeking funds for the PERCs at Campbell. We actually had $10 million in the bank, thanks to Nancy's work getting qualified zone academy bonds for the school district. But the board redirected those funds. So we went to the California Energy Commission, as did many other fantastic projects, seeking an EPIC grant for $5 million. We were not funded. And right now we're seeking funds from the Federal Energy Management Agency's 404 Hazardous Grant Mitigation Program. And it's kind of an interesting program. It's a rolling program. It has variable funding. There's a number of eligible categories: soil stabilization, wildfire mitigation, flood diversion. Generators are one of about 20 different eligible categories. And generators in the past have meant diesel gensets with a tank of fuel. And so we're bringing to FEMA something completely different: carbon-free microgrids that don't have tanks of fuel that can run out. We're bringing carbon-free microgrids that can operate indefinitely if need be. We're also bringing a multiple location application, 3 campuses. We're addressing multiple hazards: earthquakes, fires, flooding. Maximum funding from the FEMA grants is $3 million. Minimum match is 25%. And the only hitch is that an application must come from a jurisdiction that has a local hazard mitigation plan. So we did not have one at Campbell, so we partnered up with Santa Clara County. So looking at this inverted triangle, we start at the top, we apply for funding, and we must go through an eligible sub-applicant. In our case, the eligible sub-applicant is a local government. It's Santa Clara County, which has a local hazard mitigation plan. We, in partnership with the county, are applying to the state, which is the California Office of Emergency Services, and in turn, Cal OES takes projects that they feel are viable and beneficial to our community to FEMA. So at this point, we have gone through, I'm going to the middle of this slide because we're running a little short on time, but we have gone through the notice of intent phase back in April. We were welcomed with Santa Clara County to submit a grant sub-application. We just did put together an enormous sub-application with the county and filed it on September 4th of this month. Now Cal OES can request additional information up till January, and then they will hopefully forward our application to FEMA and hopefully fund our project. Key lessons learned. There's 5 of them. The first one is shoot for the stars. The challenge at SRUSD really seemed untenable. What they were asking for was unrealistic. They didn't have anywhere near enough money to achieve these goals. But the board and its administration there, they pushed for solutions. They had a lot to learn and digest before they were ready to sign the PPA and to make a 25-year commitment. They were shocked and proud that their school district is the first one to do this and to create PERCs and carbon-free microgrids as we've done. The job required patience and great flexibility on behalf of the school district. I give tremendous credit to Dr. Shelley Moore there, the superintendent. There were unknown factors that we'll all deal with when we do projects like this, like what is the cost of upgrading the switchgear? And benefits, like what about the S-chip incentives that we were applying for that we didn't know whether we would get them or not? There were timing issues, the rate issues that Michael talked about, and interconnection issues. The board accepted the unknown values of asset management. And they never heard of it, but they accepted, they trusted and they shot for the stars, and they got exactly what they want. Blending resilience and solar to bring costs in line was essential. Batteries are too expensive on their own. You need some way of wrapping them together. Batteries or resilience is like insurance. It's only valuable during the catastrophe. And who wants a catastrophe? So resilience could be paid for separately, but in this PERC model, this is new. We're bundling together solar and storage to be able to incorporate resilience into a power purchase agreement. And in this case, at parity. For districts that already have solar, Jiggershaw and I had a really fascinating discussion of blending energy efficiency together with resiliency to try to achieve that same effect, a bundled solution. Technology flexibility was needed to seal the deal. I mentioned that the district wanted to use vanadium flow batteries. That didn't work. They were deemed unfinanceable. And ultimately, the district had to accept a more standard battery technology to get the job done.
And another lesson was that rates always change. You know, we encouraged the district to adopt the A6 rate because it would be grandfathered, and it would be great to count on that rate, that it keeps working in the way that you're used to. But we found out later that they were grandfathering the time periods, locking those in, but they also are changing the rate structure. So it is going to shift the cost a bit. So it would be better. We think it would be better if you could count on these for long term. And we need rates that reward solar and that make solar prosper.
And the last lesson that really ties to that is this need for regulatory reform. And I've heard several people say, you know, to develop microgrids in California right now is pretty risky business. You know, the costs are high and the interconnection requirements are complex. So we're very excited about SB 1339. And just to add a little bit of color to this, our systems were completely connected in January of this year. And it took until just a few weeks ago to get the final permission to operate from the utility. So it was an 8-month period just for the interconnection. State policy promotes microgrids. The CEC has had fantastic grant solicitations, to $26.5 million in 2014, $47 million this past year. But microgrids have been stymied by this unclear regulatory path. And the SRUSD case study makes it clear that there's a strong need for consistency and simplicity and streamlining of the interconnection regulations. So we're excited about SB 1339. It's intended to bring more predictability to microgrid development and to their benefits. It will require utilities to take action to support, even creating special tariffs and streamlining interconnection standards and permitting requirements. We've done quite a bit of research. We're happy to share with you. When we first started getting into this, we put together a white paper called the Lithium-Ion Hybrid Electric Building Revolution. A lot of discussion. I don't believe that lithium-ion is the best storage solution. There's lots of other storage solutions, but it's certainly stolen the day. And it is popular and profitable right now. We've created a white paper on creating microgrids and PERCs back in April of last year. We then dug in on ancillary services from distributed storage so that we could explain to the school district these values. And we've just recently released, just a couple days ago, a major case study that goes along with the video that I talked about. So at this point, we're open to some questions and answers. Grace?
Great, thank you, Ted. That was a fantastic presentation. We hope that all participants were able to find it valuable and worthwhile. The first question we have here is, how is the pricing in markets for ancillary services developing?
I think the answer is that they are being developed. The PERC had a ruling last year that required ISOs to buy ancillary services all the way down to the 500 kW level. The level had been higher than that before, and I think the PERC in that determination recognize that you can turn on a battery, or you can discharge or absorb energy in a battery in a few nanoseconds, while it takes 10 to 15 minutes to fire up a combined cycle gas turbine. I don't know the exact timing of when we'll be able to sell these services to the California ISO, so we'll just keep you posted on that.
Great, thank you. And then the next question we have is, how long can a battery store energy? Is it diminished if it's not used?
Well, it does have a degradation rate. There's some inefficiencies in converting the DC power into AC power and vice versa, and batteries do degrade over time. We think in terms of the lithium-ion battery having about 10 years of life, and that will degrade a little bit over time. So if end of life, let's say, is at 80%, you might want to oversize it at the beginning so you have that amount, and then you have to consider what to do with its afterlife. Contrast that with other technology like vanadium flow, where you're basically using an exchange of fluids, and those have more like 30-year life. So, but different efficiency factors. So it's a mix with different technologies.
Great. And then, were there any energy efficiency projects introduced as an option to reduce load for the schools?
Actually, the good question, because we always advocate energy efficiency first before you get into any sizing. And a lot of the district had already worked with the Monterey County Office of Education to do extensive lighting retrofits on the campuses. So we were very comfortable that they had done pretty much everything that was cost effective before we got into the microgrid development.
Great. And how does EcoMotion's consulting services work? For example, project-based, hourly, and what is the approximate percentage of consulting fees of a total project cost?
Good question. We're happy to work in different ways. We're a consulting firm that I think is best at figuring out where the clients are at. And I can tell you that with the Santa Rita project, we spent months and months cultivating the project, educating the board, educating the school district. And at that point, we were working on an hourly basis. As we got into the project and putting out the project to bid, we shifted over into a project basis instead of an hourly basis. And I would think that our fees came in at well under 5% of project costs. I'd have to go back and calculate it, but probably in around the 2% of total project costs.
All right, great. And I will send the remaining questions to you, and then we'll send that out to all participants. And as a reminder, the webinar is recorded, and the PowerPoint presentations will be shared via email by the end of this week, and also posted on the LGSCC website. If you have any additional questions for our speakers today, please don't hesitate to reach out. We hope that you will be able to join us for our next webinar, which will discuss resilience in buildings and feature DNVGL's Be Ready tool. More information on that webinar and our upcoming forum on disasters and energy resilience will also be shared via email. And that concludes our webinar. Thank you again for joining us today, and thank you for EcoMotion for presenting.
Well, thank you very much, Grace, and thanks to Margaret also at the LGSCC. I'd like to thank EcoMotion's business coordinator, Michelle Baldy, for technical assistance with the webinar. And thanks to you all, and be in touch, and have a great day.
Thank you.